Today we shall discuss about clipping and clamping circuits, which are some circuits. Those are built from diodes and resistors and capacitors together in order to shape certain waveforms. When we do not want the complete waveform, or suppose we want to clip one portion of the waveform which is given as input, or we want to clamp the DC level of a waveform at certain higher level than what actually is, these clipping and clamping circuits are used. So, basically these are wave shaping circuits which are made from diode and resistors or capacitors generally built into a circuit, and these clipping and clamping circuits find applications in many areas of electronics. For example, in communication, then in control and instrumentation circuits, etc., we sometimes require some particular or special waveforms, not like general waveforms like sinusoidal, etc. So, to build these waveforms, we will use diodes, both normal and Zener diodes are used. So, today we will be discussing about these clipping and clamping circuits, which are nothing but wave shaping circuits. So, diodes can be used in wave shaping circuits. These either limit or clip portions of a signal or shift the DC voltage level of the signal. So, these circuits which clip a portion of the waveform are called clipping circuits, and those circuits which clamp the DC level at some other value are called clampers. Now, in order to understand clipper circuit, let us first take an example of a clipper circuit using an ideal diode. First of all, we will be discussing a clipper using an ideal diode for simplicity and easy understanding. Then we can go for actual diodes. So, this circuit here, this is ideal diode having the threshold voltage 0 and the diode forward resistance 0. Input which is applied to this circuit is, for example, a sinusoidal wave is given. Now, this circuit has a resistance R and this is the diode, and at the end side of the diode is connected a battery. Positive terminal is to the N side, and this battery has a magnitude of VB say. Now, we want to find out the voltage waveform at the output, which is V naught t. Suppose we want to plot V naught t and VIT, that is given a sinusoidal waveform to the input. What will be the output? With these polarities, we will be denoting this output signal. This point is higher with respect to this is actually ground point. So, now in this circuit, we have to first see when the diode will be conducting. Now, this diode has on the N side a battery which is having the potential VB. Now, in order to conduct, the voltage at P side must be higher than the voltage at N side. That means, VIT magnitude at any point should be higher than VB, so that the diode conducts. Now, VI is a sinusoidal waveform as shown here. So, now the voltage at any instant will be varying as shown in this plot. Now, suppose we consider in this half cycle when the VI rises, then till the point VI is less than VB, this point is at a lesser potential than this point, then obviously this diode will not conduct. That means, we have a non-conducting diode for those portion of the input voltage waveform till the point Vi is less than Vb. So, when Vi is less than Vb, this is at a lesser potential than this point, P is at a lower potential than N point. So, the diode does not conduct, it is like an open circuit. So, this part is like an open circuit. So, the voltage if we want to find out at these 2 points, then this point and this point across which we are finding this voltage. So, the 2 points are nothing but these 2 points, since this circuit is now not the current is not conducting, this point and this point are same as this point and this point, there is no conduction of current, so there is no voltage drop. So, the voltage V naught t is equal to Vit for the portion of the input voltage waveform when Vi is less than Vb. So, the Vi and V naught will be just coinciding, or it will be same voltage Vi and V naught. Now, when Vi is greater than Vb, this P is at a higher potential than N, because N is connected to Vb and this is now higher than Vb. So, now the diode will be conducting. So, when the diode conducts, then what will be the voltage across these 2 points, that is we want to find out V naught t. Since we are assuming that the diode is ideal, the diode drop is 0 and the resistance of the diode is also 0. So, this voltage V naught with this point higher than this point, that means with these polarities, what will be the voltage V naught? V naught will be equal to Vb. So, that is shown here, this is V naught equal to Vb when the diode conducts. Now, you note that the sinusoidal voltage Vi is varying, and from this point downwards, now Vi is less than Vb. So, when again Vi is less than Vb, the diode will be off. So, the diode is non-conducting, there is no current flow, this voltage V naught t will be equal to exactly Vit. So, from this point again till when Vi is greater than Vb, up to this point input and output voltage are same. Again it will be conducting when Vi is greater than Vb. So, the output voltage V naught will be equal to this Vb voltage, and again this will be continuing like that. So, you just note here that the upper portion of the input voltage is now clipped. We are getting a output voltage V naught which is like this. So, this portion is just clipped away from the input voltage. So, this is a very simple example of a clipper circuit. Here you notice that we are still assuming that the diode is ideal without any voltage drop when it conducts and resistance being 0. But now if we consider the diode having the voltage drop Vd naught, that means suppose we consider now another example where we have a diode which has an equivalent constant voltage drop model, and let us see an example of a clipper circuit using a constant voltage drop model of a diode. That means a diode which has Vd naught is equal to say around 0.7 volt for silicon. So, this example here we have this diode which has Vd naught drop and Rd is ignored again, that is resistance of the diode is very small, we ignore here. That means we will be using the constant voltage drop model for the diode. Now, this circuit is having this diode which is now connected to a battery Vb, Similarly to this example, that is N is connected to positive of Vb. The same example, if we now consider that the diode is not ideal, but it has a voltage drop Vd naught. Now, what will be this output voltage V naught t for the input voltage sinusoidal voltage that is being given? In earlier case also we are using sinusoidal voltage. So, now also suppose we give an input voltage sinusoidal, find the output voltage for this circuit. Now, the easiest way to deal with such circuits and to plot the output versus input is to draw the equivalent model for the diode. That will be simplifying the circuit. Instead of just considering this diode and assuming Vd naught as a diode drop, we will be drawing the circuit again with constant voltage model for this diode, that is having Vd naught 0.7 volt or 0.3 volt as the case may be. So, let us generalize it having Vd naught as the diode drop, and we redraw the circuit using equivalent model for this diode. So, this same circuit, if we draw the equivalent model for this diode and replace it along with an ideal diode, that is what is done for equivalent model. If you remember, what we have done earlier is that when you want to replace the diode by its equivalent model, we draw the battery showing the drop Vd naught along with the ideal diode. Ideal diode is just to show the direction of the conduction current in the diode. So, the same circuit we are equivalently drawing again by using this constant voltage drop model Vd naught. Others are same, Vb is there, this source battery is there. So, input voltage is sinusoidal, again we are assuming. Now, in this case, now you find out the condition when the diode will be conducting, that is Vi is sinusoidal, it is varying with time up to a peak value, it will be increasing then decreasing to the negative peak and it will be continuing. So, at any instant, in order to know when the condition for the diode to conduct, we must see when this P is at a higher potential than N. So, we are applying the voltage Vi. Whenever Vi is higher than the potential at N point. Now, what is the potential at N point? This potential is Vb plus Vd naught. If you find out the potential at this point with respect to ground, what will it be? This Vb is already there. So, Vb, again this is the diode drop. So, minus plus it will be in series totaling up to Vb plus Vd naught. So, P, the potential at P must be higher than Vb plus Vd naught. When this happens, then only the diode will conduct. So, whenever Vi is greater than Vb plus Vd naught, then the diode will be conducting. Now, when the diode conducts, what will be the voltage across these 2 points, that is with this potential being higher than this potential, that is the way we are denoting V naught T. Conventionally it is denoted like that, this potential is negative is a ground actually. So, V naught is equal to when the diode conducts. Now, this is ideal diode because that is normally we replace the diode by its ideal diode and battery Vd naught. So, the voltage V naught T when this will be conducting, that will be this voltage. So, with respect to this point, what will the voltage at this point? Vb plus Vd naught. So, when the diode conducts, the voltage will be constant at Vb plus Vd naught. And when Vi is less than Vb plus Vd naught, then the diode will not conduct. So, when the diode is not conducting, these 2 points are like open circuit. So, there is no path of current through this. So, that means these 2 points are open circuited. So, the voltage at this point is same as the voltage at this point, means output voltage is equal to the input voltage. Since there is no current flow, there is no resistance, there is no voltage drop across this resistance. So, input and output voltage same. So, now we can draw the input and output voltage waveforms. Vi is the input voltage, which is sinusoidal. Suppose it has a peak value of Vm, and we want to draw V naught along with this Vi, superimposing on Vi, then we will be getting, that is denoted by this green line, this is the output voltage V naught T. So, till the point when input voltage is less than Vb plus Vd naught, the diode does not conduct. So, input and output voltage are same, and whenever Vi is greater than Vb plus Vd naught, the diode conducts and the voltage V naught will be equal to Vb plus Vd naught. We get a constant voltage across the output terminals. So, V naught will be Vb plus Vd naught. Then from this point downwards, again Vi becomes less than Vb plus Vd naught. So, we have the diode not conducting. So, output voltage and input voltage are exactly equal, and this will be continued like this. So, we see now the effect of that Vd naught, that is the diode drop, which was earlier ignored in the first example, but now we are considering. So, if you compare these two plots, here it was cut at Vb, that means upper portion from Vb was clipped, but as because of this diode drop, now the upper portion from Vb plus Vd naught will be clipped. So, this is a typical example of a constant voltage model drop considered for the diode, and this is a simple clipping circuit, clips a portion of the waveform, upper portion is clipped. So, we can design different clipper circuits according to our need. I mean, if we want to clip an upper portion like this at this voltage, then we can design the circuit like this, or suppose we want to clip both upper and lower portion, then also we can design it. So, we will be now showing some more examples to illustrate different clipper circuits. So, now before going to another circuit, again let us consider the same circuit, and one important characteristic let us discuss, that is transfer characteristics. So, transfer characteristics is basically a plot between the output voltage and input voltage. You have to be careful because both the axes are involved, that is input voltage we plot in the x axis, output voltage if we plot in the y axis. We have to now plot V naught versus Vi, that is called a transfer characteristic. Now, for this particular example, if we now plot the transfer characteristics from this output waveform versus input waveform, we see that till the point input voltage is less than Vb plus Vd naught, output and input voltages are equal. So, output and input voltage will be having a linear relationship with a slope 1 like that, as is shown here. So, here on the straight line passing through this origin, the voltage input and output will be same, and it will be continuing till the point when Vi is greater than Vb plus Vd naught. So, when Vi is greater than Vb plus Vd naught, the voltage is constant at Vb plus Vd naught. So, that is why it will be constant, and whenever Vi is less than Vb plus Vd naught, it will be bearing a linear relation with slope 1, that is shown here by this red line, that is this portion is for the non-conducting portion of the diode, that is from this point onwards the diode is conducting, voltage drop is constant at this voltage Vb plus Vd naught. So, this portion is the non-conducting portion where input and output voltage same, defined by this straight line passing through the origin having slope 1. So, now this is an important characteristic which we can draw from the input and output voltage waveforms. Now, let us consider another example. Here you have to just note that this 4 volt battery is there which is connected in such a way to the diode that its positive terminal is connected to P, and suppose we are applying a triangular voltage at Vi. Instead of sinusoidal which we have discussed, let us now apply a different voltage waveform, triangular waveform with the peak value of 16 volt. That is, this triangular voltage waveform has a peak magnitude of voltage of 16 volt. Here also you have to assume Vd naught equal to 0.7 volt, that means it is a silicon diode. Rd is again ignored for all practical purposes because we are dealing with resistances which are generally having high value, and we can neglect this Rd which is very small, that is the forward resistance of the diode. So, in this case if we now look into the condition for conduction of this diode, as we can see already this diode is being forward biased by this 4 volt, that is this P is connected to positive. Now, input voltage is a triangular voltage. Now, when it will be conducting, that diode will be conducting when we have this voltage at the point P being higher than the voltage at the point N, and you see here N is being applied a voltage, and if we consider now this conduction, let us first draw this equivalent circuit for this diode as earlier we have done. So, this diode drop Vd naught, it will be along with this ideal diode which shows the conduction direction, and this 4 volt battery is already there, we are applying a triangular voltage waveform. So, this diode will conduct current when the voltage at this point is higher than the voltage at the end point. So, the potential at this point P of the diode is how much? It is from this point, if we see 4 minus plus, that means 4 positive, in the direction it is minus 2 plus, it is positive, and this is again plus 2 minus, it is negative. So, 4 minus Vd naught, this voltage must be greater than the voltage at the end which is Vi. So, the condition is 4 minus Vd naught should be greater than Vi in order that the diode will conduct. We can just write in another way that Vi is less than 4 minus Vd naught. Since we have been told that this is Vd naught is 0.7 volt, 4 minus 0.7 becomes 3.3 volt. That means we get a condition that when the voltage, input voltage Vi will be less than 3.3 volt, then the diode will be conducting. Whenever it is greater than 3.3 volt, then it will be not conducting. The moment it becomes greater than 3.3 volt, you can see that this will be reverse biased. So, it will be not conducting. So, we now get output voltage plot versus input voltage plot. This input voltage is triangular voltage having peak value 16 volt. So, the output V naught if we draw. So, we have seen that when Vi is less than 3.3 volt, it will be conducting. Now, when it conducts, what will be this voltage? This voltage is nothing but from this point 4 volt positive minus 0.7 volt means 3.3 volt. So, it will be clipping the output voltage will be clipped at 3.3 volt when the diode conducts. So, we get the output voltage as a constant voltage for the conducting part. So, this will be constant when the input voltage is less than 3.3, that means this is the conducting region, and when the input voltage is greater than 3.3, the diode does not conduct. When the diode does not conduct, you can see here, when the diode does not conduct, that means input voltage is greater than 3.3, it will be not conducting, and when it does not conduct, this is like open circuit, the output voltage and input voltage are equal. So, we get output voltage and input voltage just overlapping for the reason when the diode does not conduct. So, this will be the output voltage plot that we have drawn with respect to the input voltage. So, in this case you see that this portion, lower portion, this portion is clipped. The lower portion, when the voltage is less than 3.3 volt, this portion is just clipped away. So, this is another example of a clipper circuit. Now, let us take example of another circuit. Here two diodes are there. The diodes are connected in such a fashion, and there are two batteries VB1 and VB2 being connected to these two diodes with these polarities as we see here in the diagram. Let Vi be sinusoidal again. Find what will be the output voltage. With these polarities we are denoting the output voltage. Now, here also we will be considering a constant voltage model for the diode, that is diode drop is Vd naught, and we have to ignore the forward resistance of the diode Rd. So, now as it is easier to deal with such circuits if we replace the diode by its constant voltage drop model, we will be doing that. So, this circuit we are drawing again by replacing the actual diode by its constant voltage drop model, that is shown here. So, this diode D1 and this is diode D2. So, this diode has a drop, both these diodes actually have drop, same drop Vd naught. So, Vd naught along with the ideal diode with the conventional way of denoting the polarity of the Vd naught, that is the diode conduction is in this way. So, Vd naught will be having positive polarity here and negative polarity here. So, this is the way of showing the equivalent model with the battery polarities like this. Similarly, other diode conduction is in this direction from bottom to top. So, the diode drop Vd naught will be also having the same polarity, that is positive here, negative here, this is Vd naught, and the other voltages batteries Vb1 and Vb2 are as it is we have drawn, and these are ideal diodes. So, we are now to find out what is the output voltage for a given sinusoidal voltage Vit. Now, let us consider a positive half cycle of the input voltage, that is positive half cycle when this point is at a higher potential, positive potential than this point. So, when it is positive, you see this Vb1 and Vb2 are connected in such a fashion that they are already reverse biasing these diodes. That means, this Vb1 is positive is connected to N, here negative is connected to P, that means both are connected in such a way that both the diodes are already reverse biased. So, it will be depending now on the polarity and the magnitude of the input voltage when it will be conducting. So, in order to conduct, if we consider a positive half cycle of the input voltage, when this point is at a positive potential than this point, then it will be diode D1 will be conducting when this point P as is at a higher potential than this point. Now, What is the potential of this point N? It is VB1 plus VD naught, minus plus minus plus, that is series. Two batteries are in series with this point negative, this point positive. So, VB1 plus VD naught is potential here. So, when Vi is greater than VB1 plus VD naught, then this diode D1 will be conducting. But as you can see here, this diode D2 will not conduct in that half cycle, because here in the positive half cycle of the input voltage, this diode is reverse biased, and this battery is also connected in such a way that this VB2 is reverse biasing. So, there is no question of conduction of current the diode D2 in the positive half cycle. So, in the positive half cycle of the input voltage, when the input voltage is higher than VB1 plus VD naught, then the diode D1 will conduct. In the negative half cycle again, if we see, the diode D2 will be conducting, this diode will be conducting when this magnitude of Vi is higher than the magnitude of VB2 plus VD naught, because it is in the negative half. So, negative half of the input half cycle will be such that whenever this point potential is higher than this potential, which is VB2 plus VD naught, but with a negative sign, because we are considering negative half cycle. So, magnitude, that is why it is written here, magnitude of this Vi must be higher than the magnitude of this total voltage in the negative half cycle we are considering. And when this diode will be conducting in the positive half cycle with this condition, then output voltage will be simply this plus this VB1 plus VD naught. Similarly, in the negative half cycle, when this diode will be conducting, for this condition to be satisfied, that Vi is greater than VB2 plus VD naught, if we find out this voltage, it will be this voltage plus this voltage, but with a negative sign in the negative half cycle. So, now we can draw this output voltage waveform versus input voltage waveform. Input is this black one, Vi, and if we now find out and plot the V naught, this is 0 starting with this. So, when input voltage half cycle is positive and input voltage is less than VB1 plus VD naught, the diode does not conduct. When the diode does not conduct, then this voltage is same as the input voltage, because there is no conduction of current, there is no drop here. This 2 point and this 2 point does not have a change difference in potential. So, V naught will be equal to Vi for this portion. Now, whenever Vi is greater than VB1 plus VD naught, the diode D1 conducts and the voltage will be equal to VB1 plus VD naught, that is why it will be constant. Then again, when Vi is less than this voltage, the diode D1 will not conduct and input voltage and output voltage are same. It will be continuing in the negative half cycle. When Vi is greater than VB2 plus VD naught, then this diode will D2 will conduct, and when D2 conducts, the voltage will be VB2 plus the diode drop in the negative half cycle, that is shown by this constant portion. So, this whole green curve will be showing the plot of the output voltage V naught. So, we see here an example where both the input and both the upper and lower portions of the waveform, input waveform are clipped away. So, this is upper portion, this is lower portion, both are clipped. Now, this depending upon the magnitude of VB1 and VB2, this voltage waveform will be, it will not be symmetrical, because VB1 and VB2 when they are equal, then only it will be symmetrical. Otherwise, we can have asymmetrical waveform. If VB1 is higher than VB2, then we will be getting an asymmetrical waveform, or even VB2 is higher, then also. So, depending upon which voltage is higher, this portion will be higher or lower where the diode is clipping. So, this is another example. Now, let us take one more example of a clipper circuit. Now, here in this circuit we have to find V naught and we have to assume that the diodes are ideal, D1 and D2 are ideal. So, as D1 and D2 are ideal, this drop is 0 here, this also drop is 0 here, and the resistances are ignored, that means they are 0 for both the diodes. So, now in this circuit, now we have to find out V naught. We are applying a sinusoidal wave, Vi is equal to 6 sin omega t. So, 6 sin omega t has a peak value of 6 volt, it is a sinusoidal waveform having a peak value of 6 volt. So, what will happen to these diodes when you apply this voltage? Now, you have to be careful because we have two batteries, 2 volt and 4 volt are connected in this fashion. With D1 2 volt battery is there, which is reverse biasing this diode, and this voltage 4 volt is also reverse biasing this diode D2. So, both these diodes are reverse biased by these two batteries. So, now when it will be conducting? So, from 0 to 2 volt input voltage, when input voltage is 0 to 2 volt, that means less than 2 volt, then the diode D1 cannot conduct, and in the positive half cycle when Vi is less than 2 volt, then there is no possibility that diode D2 will conduct because it is reverse bias already, and in the positive half cycle of Vi up to say Vi is less than 2 volt, it is also reverse biasing this diode D2. So, in the positive half cycle if we consider and consider the portion when Vi is less than 2 volt for 0 to 2 volt say, we find that D1 and D2 both are off, both are not conducting. So, both are reverse bias and both are not conducting. What will be the output voltage? Output voltage is equal to the input voltage, exactly equal, since these are ideal diodes consideration. There is no voltage drop in the diode as well as no resistance. So, in output voltage will be equal to input voltage for the portion when input voltage is less than 2 volt. That means, if we consider voltage waveform, input voltage waveform Vi sinusoidal, this is 6 volt. Then from 0 to 2, this is time, suppose 2 is here. So, when from 0 to 2 you will not find any of the diode conducting, V naught and Vi are exactly equal, this up to this portion V naught and Vi are equal. Now, what will happen? This is from 0 to Vi is greater than 0 less than 2 volt. Now, when Vi is greater than 2 volt, in the positive half cycle when it is greater this portion, so when it is greater than 2 volt, this diode D1 will be, this diode will be conducting. So, this diode is conducting. So, when this diode conducts, current will flow in this circuit. The other diode does not conduct even now because it is in the positive half cycle, it is being reverse biased. So, this diode is conducting. So, when this diode conducts, what will be this voltage? That can be found out if we find out the voltage drop across these 2 points. So, if we want to find out what will be the voltage drop across these 2 points, this 2 volt and this is 0 drop in the diode. So, it will be, current will be flowing in this direction, this point is positive, this point is negative. So, with respect to this ground point, what will be the voltage that is asked? So, this is 2 again plus I into R2 minus plus minus plus. So, from with respect to this point, the whole voltage across these 2 points is 2 volt plus I into R2. Now, what is I? That has to be found out. So, what is I? I is equal to Vi minus 2 divided by 10 plus 10k, 20k. So, when Vi is greater than 2 volt, D1 turns on, and this I1 we find out, this is Vi minus 2 divided by 10 plus 10 kilo ohm. So, now let us find out what is this voltage drop V naught when this diode is conducting. This diode is conducting. So, the voltage with across these 2 points is 2 volt plus this drop, because as the current is flowing in this direction, the diode conduction will be in this direction. This point is positive with respect to this point. So, what will be the voltage at this point with respect to ground, that is 2 plus I1 into R2 minus plus minus plus. So, total voltage is summation of these 2 voltages. So, what is this current? Vi minus 2, just applying Kirchhoff's voltage law, Vi minus 2 divided by 10 plus 10, it is in kilo ohm. Now, Vi is a sinusoidal waveform. So, what we can find out? Only we can find out the slope, and from that we can find out the shape of the output voltage. Now, for that we first of all replace this I1 Vi minus 2 by 10 plus 10 20 into R2 is 10 plus 2. This gives, after simplification, Vi by 2 minus 1 plus 2, that is Vi by 2 plus 1. So, depending upon what is the Vi at any particular instant, it will be giving you the output voltage. So, if Vi we consider the peak voltage, that is if we consider the peak point, let us consider the limiting points. One is starting from 0, it will be sinusoidal waveform is 6 volt is the peak, Vi is 6 sin omega t. What will be this voltage at 6 volt? You put this value of 6 by 2 plus 1, that is 4 volt. That means, when this voltage input voltage is 6 volt, your output voltage will be having a value of 4 volt. So, it will be like this. So, now we get the, for the positive half cycle we get the output voltage waveform. Now, when the other diode will be conducting, now this diode is being reverse biased by 4 volt already. So, in order to conduct, then up to minus 4 volt, that is in the negative half cycle if we consider, because in the positive half cycle it cannot conduct at all. So, when the input voltage will be in the negative half cycle, then till the point when the input voltage magnitude is less than 4 volt, then this diode will not conduct, D2 will not conduct. When the negative voltage has a magnitude greater than 4 volt, then it will be conducting, this diode will be conducting, this point is at a higher potential than this point, in a negative half cycle we are considering. So, the diode will be conducting, and then when this conducts or this diode D2 turns on, what will be this voltage? The voltage across these 2 points, as this diode is ideal, there is no drop. So, this voltage is nothing but minus 4 volt. The voltage here, you see this point and this point, when the diode is turned on, it is like this ideal diode does not have a drop. So, it will be simply this type of circuit at these 2 points. So, V naught T, with this polarity we are considering what is V naught, this is 4 volt. So, this point is positive, this point is negative. So, it is a falling volt, falling direction, plus to minus. So, V naught with respect to this point is minus 4 volt. So, V naught is minus 4 volt when the diode is D2 is turned on. So, now combining all this, we can now draw the output voltage waveform versus input voltage waveform. So, it is like input is this one, black one, output will be the green one. So, when from 0 to 2, it is input and output same, and at input is 6 volt, output voltage is 4 volt, we have found out. And again, when it is less than 2, it will not conduct, till the negative half cycle, when it is the magnitude of the input voltage is greater than 4 volt. That means, it is more negative than minus 4, then only it will be conducting, and the voltage will be, this voltage will be minus 4 volt, it will be constant voltage drop. So, this will be again, when Vi is again less, it will not conduct, input and output same. So, we will be getting such a waveform. This is also clipped, but the difference between earlier one and this one is that here we are not having a constant voltage drop, but there is a slope. So, this waveform is similar to a sinusoidal waveform, but the lower portion we are getting a constant clipping. So, this is a difference than the earlier circuits that we considered. So, V I and V naught plot will be like this. Now, we can draw the transfer characteristic also for this plot. So, if we plot it V naught versus V I from 0 to 2 volt, as we have seen, output and input voltage are same. So, having a straight line relationship with slope 1, tan theta is 1, output and input are same. So, this will be a straight line passing through the origin up to 2 volt. When it is greater than 2 volt, from this point to the peak point when V I is 6, the voltage at the output is 4. So, these 2 points you can just connect. To get a straight line, only two points are needed, minimum 2 points. So, we connect these two. This will be the slope for this portion of the input voltage, that is when input voltage is greater than 2 volt. In the negative half cycle, again up to minus 4 volt, input and output voltage are same, because the diode D2 is not conducting. So, when the diode D2 is not conducting, here you can say see, when it is not conducting, these 2 points are same as these 2 points, since there is no drop, there is no current. When the diode D2 is not conducting in a negative half cycle, this cannot conduct because it is already reverse biased by this, as well in the negative half cycle, again it will be reverse biased, P will be connected to N. So, we get input and output voltage same for this portion, that is why it is a straight line having slope 1. But when it is crossing that minus 4 volt V I, it is greater than its magnitude of the reverse voltage is greater than 4 volt, then diode D2 will conduct. When diode D2 will conduct, the output voltage V naught is equal to that voltage minus 4 volt. So, it is constant at minus 4. So, this characteristic is called transfer characteristic. This discussion, whatever we have done, is about the clipping circuit, which clips a portion of the waveform given to you. Now, another circuit which is of practical importance is clamper. Now, clamper is a circuit which will be clamping the DC level of a waveform at a different value than what is actually the level. Suppose we consider a sinusoidal waveform. If it is periodic sinusoidal waveform like sin omega t, then its average DC value is 0. But this average DC value can be clamped at some other value, that DC voltage can be shifted by clamper circuit. A very simple example of this clamper circuit we will be showing here, having an RC, that is a capacitance and a resistance. It is connected like this as is shown in the circuit, and a diode. And let us, for simplicity, easy understanding, we consider first of an ideal diode. Ideal diode is having 0 drop and resistance is ignored. We are applying, suppose, a square wave, that is this type of waveform. It is an AC, no doubt, but this peak and this peak are exactly equal and it is square. Now, one assumption is very important here that we will be making is that the time constant of this circuit, the discharging time constant RC, is very, very large compared to the time period of the input voltage. That will be important assumption that we will be seeing here later on. Now, this circuit, suppose we are applying a square waveform, what will happen? Now, when you have in the positive half cycle of the signal, so this positive half cycle of the signal, the diode will be forward biased in this half cycle. Let us consider this half cycle V, suppose we are giving a voltage, like this, V minus V. So, now we have this voltage, input voltage, and we have this capacitance. This is the diode and there is a resistance, and this is C. RC time constant is very large, that is very, very large compared to the time period of the input signal, which is Vi, this is Vi. Now, what will happen when in the positive half cycle, this capacitance will be charged because this diode will be conducting. This is an ideal diode, there is no drop, and it will be like a short circuiting, it will be conducting through this part, it will be conducting through this part. So, this capacitance will be charged to a voltage of V, and as discharging time constant is almost 0, because diode has a very negligible resistance, and in this case we have neglected that resistance. So, the charging time is almost 0, it is 0, and instantly it will be charged to a positive voltage V. So, this voltage will be V when it is charged to the peak value, instantly it will be charged. Now, in the other half cycle, negative half cycle, what will happen? In the negative half cycle, this point is negative, this point is positive, this is the half cycle. Now, this was already V, now again a V. So, across these 2 points if we consider this voltage minus plus, it will be twice V, and this diode is biased by a voltage twice V with polarity, this is negative, this is positive. So, it is reverse biased. So, the diode will not conduct, but what will be this voltage? This voltage will be equal to this plus this twice V in the negative half cycle. In the positive half cycle, what will be the voltage? When it is conducting, this diode has a drop 0. So, V naught will be 0 when in the positive half cycle. So, in the positive half cycle, V naught is 0, that means it will be 0, and V naught if we plot, this will be 0, but in the negative half cycle, this will be minus twice 2V, that is this output voltage will be minus 2V in the negative half cycle. So, that is what we will be getting if it is V and minus V are the peaks of the input voltage. Output voltage will be having a 0 voltage when this conduction takes place, because when conduction takes place we can see here this diode drop in the positive half cycle it is 0, and in the negative half cycle when it does not conduct, the voltage across these 2 points is 2V. So, we get this voltage. So, here you can see that the voltage waveform given was this one, but now we are getting a voltage where the DC level is clamped at different voltage. We are getting minus 2V, earlier it was minus V. So, we get at a higher voltage D waveform is clamped. This is the example of a clamper circuit. Now, another example let us consider of a clamper circuit. Here this one, this diode is, let us consider not ideal, it is 0.7 volt drop is there, resistance is 0, but we are applying Vi which is an asymmetrical square wave, asymmetrical wave having square wave shape, and peak voltage in the positive half cycle is 20 volt, negative is minus 5 volt. So, now what will happen for this, if we consider the diode equivalent circuit, it will be like this is the ideal diode, its drop will be in this direction 0.7 volt. Again this voltage is there which is plus minus 2 volt, and this is the input voltage, and this is the resistance. I want to find out this voltage. So, now what will be this voltage? The voltage across these 2 points is the voltage across this resistance. So, current multiplied by this resistance is the voltage. So, now in the positive half cycle when 20 volt is applied, this is 20 volt plus minus in this way it is applied in the positive half cycle. Now, when will it be conducting, you just have to see across these 2 points what will be the potential. So, here it is minus. So, this point is minus. So, it is reverse biasing, and this drop, this diode if we consider, it has a positive voltage, but that is 2 volt only. So, in the positive half cycle this voltage is, negative voltage is higher, that means this point is at a lower potential than this point, it will be not conducting. So, when it does not conduct, there is no conduction of current and this drop is 0. So, we get this 0 drop when it is in this positive half cycle, that it is not conducting. Now, in the negative half cycle, if you consider in the negative half cycle, thank you. Yeah. Now, let us consider another example of a clamper circuit. Here there is a voltage 2 volt which is reverse biasing this diode. Applied voltage is a square wave, but having peak value is different, 20 volt in the positive and negative is 5 volt peak. Now, if we want to find out when the diode will conduct, we have to find the potential across this P and N. Now, in the positive half cycle, when 20 volt is applied, this polarity is positive with respect to this. So, this point is having the N or negative of the input. So, it will be 20 volt will be reverse biasing this diode, and the potential at this total potential plus minus 2.7. So, this 2.7, but here it is 20. So, this is higher at a negative. So, this will be reverse biasing, it will be not conducting. So, when it does not conduct, the voltage across this resistance will be 0, since no current flows. If you have to be careful where you want to find out the voltage. Here it is across this resistance. In the negative half cycle, when this point is negative, this point is positive, it is forward biasing with a plus 5 volt. So, the potential here is plus 5 volt, this potential is 2.7, that is end point is having plus minus 2.7. So, here this point is having a higher potential 5 volt than this point, it will be conducting. So, in a negative half cycle, what will be this voltage? If we apply now Kirchhoff's voltage law, V naught minus plus is rising, minus 0.7, minus 2, minus plus is rising, plus 5 equal to 0, this is Kirchhoff's voltage law. From here we get V naught minus 2.7 plus 5 equal to 0. So, what is V naught? V naught is equal to minus 5 plus 2.7 is minus 2.3. So, minus 2.3 volt you will be getting at the negative side. So, we get 0 voltage in the positive half cycle, it will be not conducting, resistance R or 10K will not have any current through it. So, this voltage is 0 in the positive half cycle, but in the negative half cycle the voltage will be clipped at minus 2.3 volts. So, this kind of a output voltage waveform we will be getting for this circuit. Now, you now consider this circuit having Zener diodes. Zener diodes are also used for clamping, clipping or clamping both. Now, this circuit is having 2 Zener diodes, and these are ideal Zener diodes, means in the forward direction the diode drop is Vd naught and resistance is 0, and it has a voltage, Zener voltage Vz. Vd naught is the diode drop in the forward direction, because in the forward direction Zener diode can conduct and it will be having the normal voltage drop like a normal diode like Vd naught. So, if you give a sinusoidal voltage, you can find what will be the output. Now, whenever the input voltage is in the positive half cycle, you see this Zener diode will be reverse biased, positive will be reverse biasing, but this diode will be this Zener diode will be acting like normal diode when this point is positive with respect to this point in the positive half cycle. But when the voltage at this 2 point is such that it is lower than the whole voltage drop across this 2 point, that voltage drop is Vz plus Vd naught. If you draw the equivalent circuit, this will be having this drop, this will be not the correct direction, the Zener will be having a drop. If plus is here, it will be breaking down. So, when it will be breaking down, when it will be greater than Vz plus Vd naught, and the voltage across these 2 points will be then Vz plus Vd naught, and in the negative half cycle this will be, when we consider this point is negative with respect to this point, this diode will be reverse biased Zener diode, and this will be a forward biased normal like diode. That is, when the input voltage is greater than Vz plus Vd naught in the reverse bias condition, then again it will be conducting and the drop will be Vz plus Vd naught. So, finally, we will be getting the output voltage clipped at the upper and lower portion with Vz plus Vd naught. This is plus Vz plus Vd naught, this is minus Vz plus Vd naught, and this will be the output voltage versus the input voltage Vi. So, in all this type of circuit, what we have to do is that simply we approximate equivalent circuit we have to draw. So, this Zener diode's approximate equivalent circuit will be a Zener voltage, and similarly this diode will be having a normal diode drop when in the forward bias and the reverse bias. The other diode will be Zener and this one will be forward. So, the total voltage you have to find out and the condition when it will be conducting. So, now today we have seen a very important application of normal as well as Zener diode along with resistance and capacitance to build circuits known as clipper and clamper, and these circuits are used in practical applications where we want to use a waveform having one portion clipped off or clamping the level of the DC voltage of the waveform at some other value than what it is.